and the area of the sphere, which is the glass of the bulb, right? It's going to be different. Just solve A and B. C you can repeat this one. Heat transfer rate divided by the area. That's what heat flux is.
Don't check on.
So filament, like I said, is a cylinder, right? And the heat is generated from the lateral part of the cylinder, right? So the area of the cylinder, which is the filament, is going to be pi dl. Okay? In the part B, they are asking heat flux from the bulb, and bulb is a sphere, right? So the area of the sphere is pi d square. Okay? That's the only difference. Right? You understand what is the difference? Only the area. The filament is a cylinder. The cylinder has a, if you want to calculate the area of the cylinder, you have to calculate first the lateral area, right? And then there is a bulb or the filament, which is a sphere. Okay? So the only difference is in the area. This is sphere. This. And this is cylinder. The filament inside. And you are only calculating the area here.
Không sao.
Not this. That is the only difference. Okay. Question 4. A 2.1 meter long, 0.2 centimeter diameter electrical wire extends across a room that is maintained at 20 degrees Celsius. The temperature of the room is 20 degrees Celsius. We have a wire, okay? Heat is generated generated in the wire as a result of resistance heating, and the surface temperature of the wire is measured to be 180 degrees Celsius. So wire is at 180 degrees Celsius, room temperature is 20 degrees Celsius. Also, the voltage drop and electric current through the wire are measured to be 110 volt and 3 ampere. Okay, this much power is generated from the wire. Disregarding any heat transfer by radiation, no radiation. Okay, determine the convection heat transfer. So the air inside the room is moving, right? So the heat transfer from the wire to the room air, it's going to be by convection, right? So ignore the radiation and determine the convection heat transfer coefficient, which is small h, okay? Between the outer surface of the wire and the air in the room. Come on. Who is going to solve? So this rod is also like the filament, right? In the first question is like the filament. So the area is going to be same, pi dl. Okay? They are asking, this question is asking the value of h, small h, which is heat transfer coefficient by convection. Everything else is given. You just have to calculate the area, okay, and heat transfer rate. Doubt? If you have any doubts, ask now. Easy, right? Just be careful how to calculate the area. Okay? This is like a cylinder. The wire is like a cylinder. Last question was, consider a flat plate solar collector placed horizontally on the flat roof of a house. The collector is 5 feet wide and 15 feet long. Okay. Average temperature of the exposed surface of the collector is 100 degree Fahrenheit. The emissivity of the exposed surface radius of the collector is 0.5. Emissivity is given. There is radiation. Determine the rate of heat loss from the collector by convection and radiation. Okay? Convection plus radiation. During a calm day when the ambient air means outside air, 70 degree Fahrenheit and the effective sky temperature for radiation exchange is 50 degree Fahrenheit. Take the convection heat transfer coefficient on the exposed surface to be 2.5. BTU is British thermal unit. Okay, per hour. Anyone? Very easy.
เขาบอกว่าเขาหน่อยใช่เนอะอันนี้
You clean and then stop. So the solar plate, right, like a rectangle.
ฝังจับนะเพื่อน
When you are dealing with radiation, you have to change the temperature in a Rankine, which is denoted by R. Okay? And the unit of the radiation is BTU, British thermal unit per hour. chapter 1 is clear. In your final exams, you will be given questions, okay, from whatever assignment I'm giving you, and also the examples that we are solving in the class, okay. Alright, so moving on, chapter 2. In chapter 1, we studied the basic definition of heat conduction, right? Heat transfer by conduction. Now we are going to derive equations if the heat conduction is happening in one-dimensional, three-dimension, and in different objects like a plane wall, a sphere, a cylinder. Alright? Okay. So this is the objective of today's lecture. So we basically have three coordinates. Okay, if you want to study heat transfer in any object available in the universe, you can assume them in one of the three coordinates. It's either going to be a sphere, either going to be a cylinder, or a plane wall. Okay, or a rectangle in 3D. Since heat transfer is a vector quantity, what is vector? What is a vector quantity? Which has magnitude as well as direction. Okay. Temperature is a scalar quantity. When you say the temperature of this object is 25 degrees Celsius, you do not say in which direction, right? So temperature is only a scalar quantity. But when you talk about heat transfer, you also want to know the direction, in which direction the heat transfer is occurring, is happening, right? So heat transfer is a vector quantity. It has both magnitude as well as direction. Temperature is a scalar quantity. Since heat transfer is a vector quantity, we use coordinate system to define the direction of heat transfer. Heat transfer in the positive direction of a coordinate system is positive, and in the opposite direction is negative. To determine the temperature at a point in a medium, we define the location of the point as, so we basically have three coordinates. If you want to study heat transfer in this type of a bottle, you can assume it as a cylinder, right? If you want to study heat transfer in this wall, you can consider it as a rectangle, right? So any sort of shape in the universe, you can use any of the three coordinates, okay? Like I said, we are not making a complex model, we are going for a simple model. So we can assume any object in one of these three coordinate systems. So when we are studying heat transfer in a rectangle, right? If we are studying heat transfer in a rectangle, the three coordinates will be in x, y, z direction. Alright? 3D. If I am studying heat transfer in this bottle, it's like a cylinder, right? So the coordinate will be r, phi, and z. Okay? If I am studying in spherical object, the coordinates will be r, phi, theta. Okay? Since it's a heat transfer, we have to include time. So small t is for time, capital T is for temperature. Okay? So just add a small t. The various distances and angles involved when describing the location of a point in different coordinate systems. So you can read a lot of writing is done in the slides. So I'm going to just cover the important ones. Then we have steady versus transient heat transfer. Okay, as you can see in the picture, the first picture, a heat transfer in steady operation is happening. In the second one, it's transient. Steady means there are two walls, right? 2 p.m. the temperature on either side of the wall is 15 and 7, and 5 p.m. it's same, 15 and 7. Okay, whatever you are using, you are using a heater or a fan, the temperature is maintained somehow. Okay, it's steady. The heat transfer is still happening, right? Whenever there is a temperature difference, heat transfer will happen, but somehow you are maintaining the temperature on either side of the wall. Okay, so it's steady. And the second is transient. 2 p.m. the temperature is different, 5 p.m. temperature is different on the either side of the wall. So it is transient. The temperature is changing with time. Steady heat transfer, no change in temperature with time at any point. Transient, variation in temperature with time at any point. Okay. So, like I said, heat transfer we can assume in 1 dimension, 2 dimension, or 3 dimension. Okay. in real life everything is 3D, right? Everything is 3D. But like I said, we do not want to complex things, right? We are using numerical methods. So if you think the heat transfer is very high in one direction and very low in the second and third direction, you can neglect the second and third direction and just assume the heat transfer in one direction. Okay? So in figure 2.5, it's a two-dimensional heat transfer. In real life, it's always 3D. It's always 3D. Okay? But we will assume two dimension because in the third dimension, the heat transfer is negligible or very less in comparison to the other directions. So the steady temperature difference, steady temperature distribution in a long bar of rectangular cross section can be expressed as X and Y. Capital T is temperature. Temperature is moving in X and Y direction. It is of course moving in Z direction as well. Okay, ideally, but it's very low. So we are going to neglect it. If the temperature variation in the Z direction along the bar is negligible, there is no change with time. Okay, so we will say the heat transfer is in two dimensions. Okay. Figure 2.6, it's a window like this. Okay, so the heat transfer is of course happening in 3 dimensions in real life. Okay, but since this surface area is too high in comparison to the height and the thickness, so we can assume that heat transfer is happening in one direction only. Okay, to not complicate our model. So in 2.6, heat transfer through the window of a house can be taken to be one dimension. Okay, we are assuming in one direction because in the second and third dimension it's very low. Heat transfer through the glass of a window can be considered to be one-dimensional since heat transfer through the glass occurs predominantly in one direction, okay, and heat transfer in other direction is negligible. All right. This is your second chapter in your book. You can go through the text by yourself as well. I'm covering the important stuff. Okay. So this is your following the books which I have already. This we are here, okay? We completed this last time, so we are here. Alright. So heat transfer by conduction, Fourier's law of heat transfer, we studied in last class, right? This formula is, you remember from the last class, right? It's Fourier's law of heat conduction. K A dt over dx. Okay, K is thermal conductivity, A is the area, alright. In rectangular coordinates, the heat conduction vector can be expressed in terms of its component. If I want to calculate heat transfer in 3 dimensions in this type of a rectangle, I am going to calculate heat transfer in each direction and then just going to add, okay, just going to add it. So I'm going to calculate heat transfer in X, Y and Z direction. Alright. The heat transfer is happening by conduction. This formula we know, Fourier's law of heat conduction, right? Okay. You see AX here, AY here, AZ here, right? So this is heat transfer in X direction, Y direction, and Z direction, right? Okay. Just the area will change in each direction, right? Calculate this and add all of these. Okay, you will get the heat transfer in rectangle. Alright. Then we have heat generation. We also covered this topic in our last class. What is heat generation? Whenever you give heat to an object, sometimes the heat is generated. Okay? In that system, in that object. For example, here the sunlight is passing through the water, right? As a result of the sunlight, the water is getting heated up, right? So that temperature in the water is heat generation. Alright? In this example here, okay, heat generation is a medium through which heat is conducted may involve the conversion of mechanical, electrical, nuclear or chemical energy into heat. Heat, okay? In heat conduction analysis, such conversion processes are characterized as heat generation. So any type of heat you are giving, okay, any type of heat you are giving in form of mechanical, electrical, nuclear or chemical energy. So let's suppose, okay, look at this example here. This is an oven, right? You are giving electrical energy to the oven, right? You are switching on and the oven is getting started. What you are doing? You are giving the electrical energy. As a result of this energy, the oven is heating up, right? So the electrical energy changed into thermal energy, right? You give electrical energy, you switch on your oven, the electricity passes from the wire to the oven and the oven gets heated up. The grills inside the oven gets heated up. Heat is generated in the heating coils of an electric range as a result of the conversion of electrical energy to heat. So any type of conversion is heat generation. Okay? In this as well, the UV radiation is changing into thermal energy. Right? UV rays are passing through the water and the water is getting heated up. So the absorption of solar radiation by water can be treated as heat generation. Heat is generated in the water. Okay? Understand? Heat generation. So heat generation, like the water is heating, right? As a result of the absorption of UV radiation. Right? There is a thermal energy in the oven as a result of the electrical energy, absorption of electrical energy, right? So everything is in 3 dimensions, like I said, right? So energy generation is a volumetric phenomena. It's happening in all object, right? It's distributed in the all object. So it's a volumetric phenomenon. Alright? Water is getting heated up, it's a volumetric phenomenon, not a surface layer, right? Only the upper layer is not getting heated up. It's a volumetric phenomenon. When you heating the oven, the air inside the oven is also heated up. So it's a volumetric phenomenon. So heat generation is a volumetric phenomenon, that is, it occurs throughout the body of a medium. When you are heating the oven, it's happening throughout. Therefore, the rate of heat generation in a medium is usually specified per unit volume. Okay? And is denoted by this. Small e, E is generation, okay? Heat generation, and V is the volume of that object. That object can be a rectangle, can be a sphere, can be a cylinder. If you are passing electrical, chemical, nuclear, any type of energy in any object and the heat is generated in that object, it is heat generation. You can calculate the heat generation in that object by using this formula. Heat generation per unit volume. It's a volumetric phenomenon. Any doubts? Any questions? Total rate of heat generation in a medium of volume V is expressed as this. You understand what I'm speaking, right? If you want me to speak more slowly, let me know. Okay. Alright. I also want you to have the books, okay, that I have posted on your this book. Okay. You see a lot of theory. So if you want to go through the theories, you have to read it by yourself. Okay. So I highly recommend you to either take printouts of each chapter and start the chapter from the beginning and read the theory by yourself. Okay, it will be more clear. Okay. Alright. So there is example 2:1 here. So whatever example we are solving in the class, they can come in your final exam. Examples can also come. Okay. Questions from the assignment can also come in your final exam. Okay. So you see the book here, at the end of the book there are all of these are numericals. They are going to be too much. If I tell you that you can get questions from any of these numericals, it's going to be too much for you as well, right? So just be 2, 7, 2, 8, 4, 2, 9, 1, 6. It's a lot, right? Okay. Alright. So there is example 2:1 here. So whatever example we are solving in the class, they can come in your final exam. Examples can also come. Okay. Questions from the assignment can also come in your final exam. Okay. So just be 148, 157, 165, yeah, 174. So about 200 questions for each chapter. So at least solve the questions from the assignment and the examples that we are solving in the classroom. Okay? I'm not asking you to solve 200 questions, right? But you must solve the assignment and the examples. Okay?
อันนี้มันเล่นของ
Alright. So the first example of this chapter is the resistance wire of a 1200 watt hair dryer. Okay? Is 80 centimeter long and the diameter of the wire is 0.3. Determine the rate of heat generation. So of course, like when we want to turn on the hair dryer, we pass some electricity through the hair dryer, right? Right? So then the inside of the hair dryer gets heated up. There is a thermal energy, the hot air, right? So this question is asking you to calculate the heat generation in this dryer. Determine the rate of heat generation in the wire per unit volume. The heat generation is happening in all of the hair dryer, right? And the heat flux on the outer surface of the wire as a result of this heat generation. Okay? Heat flux. Okay. So first, it's a 1200 watt hair dryer, right? Right? So the energy generated, total energy is 1200 watt. Understand? If I am dividing it by the volume, you see here, right? This is given, capital E. Total heat that a wire can generate is given, right? Which is 1200. You divided it by the volume of the wire. Okay? You will get the heat generation. Alright? And then just divided this total heat generated divided by the area. You will get the heat flux. Heat flux you remember, right? Heat transfer rate divided by the area. Heat transfer rate divided by the area is heat flux. Heat transfer rate can be by conduction, convection or radiation. They have given 1200 watt. Okay. So this is the total heat that it can generate. If you want to calculate per volume, you calculate the small e. Okay.
ทันแล้วอะมัน4 โมงมันเริ่มบ่าย 2 ครึ่ง
เราเรียน2 ชั่วโมงครึ่งเอง
อ๋อแต่มันจะจบเมื่อตอนไป
แล้วกูอยากไปดูน้องกูอยากไปดูเด็กปี 1ไปเลย
ไม่หรอก
แต่แป๊บเดียวเอง
ทำส่วนคนเด็กส่วนคนสองล้านเลย
ฝากจานไม่เข้าน้ำเมื่อไหร่
ก็อาจจะ
แวะไปดูแป๊บเดียวเองไม่ได้อยู่นาน
Do you want me to turn on the lights? Can you see?
เสียงจะเข้ากล้อง
ไม่รู้อาจจะไม่เหลือ
เดี๋ยวก็รู้อย่าทำเยอะ
This is heat generation.
กูตกใจนึกว่าจะเขียนว่า EX ตัวอย่าง
ไม่เขาบอกว่าเขาแค่เขาอยู่
This question is saying the resistance wire
แล้ว
of
ก็
a
เดี๋ยวจะมีโจทย์
1200
ท้าย
hair
ไม่
dryer
มันเขา
is
บอกว่า
80
เขาจบไม่ออก
centimeter long. You can hear it,
มีแค่ตัวอย่างนี้ก็บอกกันว่า
ผมบอกให้เราไปโซ่ส่งมาข้อกัน
right? Determine the rate of heat generation.
ใครจะทำมาทั้งหมดวะ
In the wire per unit volume. Okay? This. And the heat flux. the outer surface of the wire as a result of this heat generation. So when you're solving in your exam, I encourage you to write few lines when you're solving your answer. Okay? Do not start directly with the equations. Right? Try to talk about the solution. Okay? If it's okay. A 1200 watt hair dryer converts electrical energy into heat in the wire at a rate of 1200 watt. Okay? The rate of heat generation in a resistance wire is equal to the power consumption of a resistance heater. Okay? The rate of heat generation in the wire per unit volume is determined by dividing the in your exam you will be allowed to carry one A4 size paper. Okay? So I encourage you to write at least the main formulas. One A4 size paper you are allowed to carry in the final exam. So write down the formulas.
Only one page or both sides?
Both sides. You can write both sides but only one page.
แปลให้ฟัง
Okay?
วันฟอร์พอ
So
เอ
write
ฟี
down
ได้
the
ใบหนึ่ง
areas,
Không thèm à?
formulas.
เอา A4 เขาได้ใบหนึ่งจบแค่นั้น
น่ารัก
ได้
ไม่เขียนจบในวิชาจะทำให้วิชาไหม
ก็ต้องฝึกเพื่อต้องจบเอง
ถ้าสุดก็หมดอีกมั้งเพราะว่า ถ่ายภาพถามหรือว่าจดในแพดแล้วก็พิมพ์ออกมาไปสอนได้ไหมหรือต้องจดหมู่ด้วยนะ
นอนนอน
อะไร
นอน
แต่พอชีวิต
ปกติ
ชีวิตมันดีกว่า
ปกติปะ
ของมันนะ
อืม
This is very important. You might think why we are considering this as the total heat generation. Rate of heat generation in the wire is equal to the power consumption. This much power the wire is consuming, right? So this is the total. You want to calculate heat generation per unit volume. This is the total, and the total will be heat generation in the wire equal to the power consumption. This is the power consumption. The wire can consume this much power. So this is the total heat generation. You want to calculate heat generation per unit volume. So just divide it with the volume of the wire. Okay. Second is you want to calculate heat flux. Just divided it by the area. Total power that the wire can consume divided by the area. Okay. You will be get the heat flux. This is heat flux. This is heat generation per unit volume. This is total. Heat generation equal to the power consumption. Okay? Clear? Okay. Now we are going to calculate heat transfer. This chapter is all about conduction in one dimension and then in three dimension. Okay? In the universe, in our world, all the objects can be identified in three types of shapes: rectangle, sphere, cylinder. Okay? Now, if the heat transfer is happening in one dimension means we have taken the example of a glass window. One dimension means the heat transfer in the y and z direction is negligible or very small. So we can neglect. You understand my writing, right? Or do you want me to write it more clear? Okay. So this is an object here. My drawing is not that good, so I'm not going to draw this. But this is a rectangle, okay? And the heat transfer in the x direction is significantly higher than in the y and z direction, okay? So we are going to only assume that heat transfer is happening in one dimension, only in x direction. So we want to write an energy balance equation. If you remember from last class, we had written energy balance. Okay, this is your first slides from your last lecture. If you remember, we had written energy balance equation. This you remember from the last class, right? Net heat transfer entering and going out. The heat generation equals to the change in thermal energy. You must have studied only this. This is your thermodynamics. This is energy balance from thermodynamics, right? We are studying heat transfer. When we are passing something, any energy, heat is generated. So we have also included this term. So this is what this is about. Same equation, okay? This is the energy balance equation in heat transfer. We are also including this term. Okay? Alright. So we are using rate of heat conduction at x. We want to study the heat transfer only in this area. So this is x, this is delta x. The thickness is delta x. So this coordinate is x, this is x plus delta x. Delta x is the thickness. Okay? Heat is propagating from here to here. Okay? In one dimension only in x. So rate of heat conduction at x, the heat that is coming inside this line and then going outside. So Q at x plus delta x, when the heat is coming inside this element, some heat is generated, right? Let's suppose I'm giving electricity, so some heat is generated. That is plus E generation in the element. It is going to be equal to the difference, rate of change of the energy content. Okay, whatever the change is happening. This is your first law of thermodynamics. If you remove this is your first law of thermodynamics. You're just including this because we are studying heat transfer. Right? So, and also we are adding small t is time. Okay? If you remove this and you remove this is your thermodynamics. Okay? So rate of change of the energy content. What is the change when the heat is entering and leaving? The change is going to be equal. Okay? First law of thermodynamics is energy conversion. What is going inside and going outside, it is going to be equal to the change in that system. Right? Okay? We studied this here. Here. In heat transfer problem, it is convenient to write a heat balance and to treat the conversion of nuclear, chemical, mechanical, electrical energy into thermal energy. So net heat transfer, if you are giving electrical energy in a wire, in the hair dryer, okay? So you are giving that, which is Q in, the energy is going out, plus E gen is the heat generation, the heat generated in the dryer, okay, or the oven, is equal to the change in, alright? First law of thermodynamics, and we just divide it by small t. Small t is time. Okay. All right. So in your exam, I'm not going to ask you to derive the equations, right? But you should know how you're deriving the heat transfer by conduction in one direction. Okay. In a rectangle. Okay. So this can be written as, this is the rate of change of the energy time, right? The difference will be T plus del T minus T. Okay, ET. You can write this E as the MC, mass, right? You remember from here. Remember? Specific heat, mass, and temperature. Okay? So we are writing that here. MC, capital T. Mass, specific heat, capital T is the temperature. Okay? At T plus del T time minus T is the entering time. Del T plus del T is the leaving time. Okay? So this can be written as this. They have just input the mass. Okay? Which is rho A del X. Okay? So you are with this now. Then you have rate of heat generation inside the element. This can be written as heat generation per unit volume, right? Right from here. Okay? Alright? Then again input the formula for the volume. Alright? Okay. Then just input this value and this value here. Alright? Del E element here. Just input the value here, input the value here. Alright? Okay. And then when we are solving, like we want to study the heat transfer in one direction, right? In this small element, we are going to assume that del X, the thickness is very small. Okay? So we take the limit, we assume del X is very zero and small t, which is the time, is also equal to 0, nearly 0. We take the limit and then we have these equations. Okay? Do you want me to do the derivation or is it okay? You just have to input these. Okay? Okay, I will do for one system and then for cylinder and sphere you can do by yourself. Why are we doing this? If, as like after we graduate and you want to, your work requires you to study the heat transfer, okay, or if you are manufacturing a glass and you want to study heat transfer, right? So if you have these equations, okay, you can study it directly. If I give you some initial conditions that you will study in the next slides, so in that case these equations are very important. If you are manufacturing a glass and you want to study heat transfer in one direction, and that glass is like this shape, okay, it's a rectangle, alright. If you are manufacturing a bottom, then you will study heat transfer in a cylinder. So not these equations, not these equations. Okay? So you can directly study. Alright? So you should know when you are manufacturing, you should know what is the room temperature inside, what is the room temperature outside. Okay? How much is the heat generating, what type of glass you are using, right? If you are manufacturing something. Alright? And then it's equal to be change. It's an energy balance equation. This is the equation. This is only applicable for this type of shape, only for rectangle, not sphere, not cylinder. Rate of change of the energy inside here, right? That is going to be equal to mass, specific heat, temperature. Mass of this rectangle. Volume of the shape. Area. Now we substitute this value. Okay. Here. This value. Here. Okay. Substitute these values. These two. this, when you are taking the limit, you are assuming del x is nearly 0, right? So this will be changed into this, and this is heat transfer by conduction, Fourier's law of heat transfer, right? When you are taking limit small t is time to 0, this can be changed into this, right? We are using partial differential, right? Because it is dependent on two variables, right? X and t. Okay. Now very important. This all is written in your books. Okay, nothing new. Okay, so you want to study heat transfer in one dimension in a plane wall. Okay, you are an engineer and you are manufacturing a glass. Glass can be a plane wall, and the heat transfer is happening in one direction. Okay, and so how will you start? You want to study the heat transfer as an engineer in the glass. You will start with the energy balance equation, right? You would know how much heat is entering, how much heat is leaving, right? And the change in the internal energy. Okay? Okay. You know all of that. Now you have this formula, variable conductivity, constant conductivity. Okay. Conductivity is thermal conductivity.
เห็นแต่ว่าไม่ชัดมันดู
K. Okay? If you are manufacturing and your thermal conductivity is changing, there are some materials, their thermal conductivity changes with temperature. Okay, there are some materials, their thermal conductivity changes with the temperature. Alright? So if you are using a glass, you are manufacturing a plain wall, a window, and you are using a glass whose thermal conductivity changes with temperature, you want to study the heat transfer in that glass, you will use this equation, variable conductivity. Okay? So you know K value, okay? And you can, what you are trying to do, you are calculating the capital T, right? Temperature. If your glass has constant conductivity and you want to study heat transfer in your glass, right? You take this K outside, it's constant. When it's inside, it's variable, right? It's differentiable, right? When the conductivity of your material or your glass is constant, you take this K outside. It's not changing with time, so we don't need it. You take K outside and you divide the whole equation by K. Okay? Take K outside divided by K, divided by K, divided by K. This you can replace with alpha. Okay? Alright? This is when you are studying heat transfer in a plane wall. Alright? When the thermal conductivity is variable, it's changing with temperature. Okay? Now I'm asking you to design a glass and study the heat transfer in that glass when the conductivity of that material is constant. Then you will use this formula. Okay? Steady state. In steady state, then this thing becomes 0. Steady state means temperature is not changing with time, right? So capital T is temperature, small t is time, right? Steady state, this becomes 0. Okay? Alright? I'm asking you to design a glass, alright? And when you're designing that glass, you would want to study the heat transfer in that glass. You will ask me if the heat transfer is steady, and I'm telling you, yeah, it's steady. Then you use this formula. Okay? If I'm telling you no, the temperature is not steady, it is changing with time. 2 p.m. something, 5 p.m. something. In the morning the sun is very high, in the evening it's very cool, right? So temperature is changing. So then you will use this term is here, but there is no heat generation inside that glass. I'm telling you this material cannot store any heat. Okay? Whatever is coming inside, going outside. There is no heat generation. So this term becomes 0. Understand? When I'm telling you that it's steady state and no heat generation, then both of these terms become 0. This term and this term become 0. So you only have this. And most of the questions, most of the numericals, most of the numerical analysis we do, we assume this, that the heat transfer is steady and there is no heat generation. Okay? The material that we are using, it cannot store any heat. Okay? There is no heat conversion. Whatever is going inside is coming outside, and it's steady state. The temperature is also not changing with time. Okay? So you have 3, 4, 5 conditions. First, variable conductivity. So in your exam, when I'm allowing you to carry one A4 size paper, right? Write down these formulas. This, not the derivation. This, and these 3. And when you are reading the numerical, read very carefully. If there is a heat generation, okay, in that numerical, if the heat transfer is steady state or transient, whatever is happening. Okay? According to that, you will use the formula. We'll do some numericals. So this is a plain wall, right? Same thing. If you are designing a bottle, a thermos, it's a cylinder, right? So in place of XYZ, it's going to be R5Z, right? So just change the coordinates and the same thing. Variable conductivity, okay? It's R, not X. Okay? Steady state, transient no heat generation, steady state no heat generation. These are the formulas for cylinder, not plain wall. Cylinder. That's why there is R, not X. Understand? Third coordinate is sphere. Okay? So in sphere, the formulas for steady state, transient no heat generation, and steady state no heat generation is this. Alright. Now look at this numerical very carefully. When you do the numerical, it will be more clear to you. Consider a steel pan placed on top of an electric range to cook spaghetti. The bottom section of the pan is 0.5 centimeter. Okay? Bottom section, this one. 0.4 centimeter thick, has a diameter of 18 centimeter. The diameter is 18 centimeter. Thickness is 0.4. The electric heating unit on the range top consumes 800. So this is placed on a oven. Okay? And that system, that oven consumes 800 watt of electricity. Okay? 80% of the heat generated in the heating element is transferred uniformly. So there is an oven, you place your pot over it. This pot is 0.4 centimeter thick. Diameter of this pot is 18 centimeter. Okay. There is a oven. That oven consumes 800 watt. Okay. And 90% of that power is given to this pot. Okay. 80% of the heat generated in the element, 80% is transformed uniformly to the pan, assuming constant thermal conductivity. Thermal conductivity is constant. K is outside. Constant. Okay. Obtain the differential equation that describes the variation of the temperature in the bottom section of the pan during steady operation. So first, thermal conductivity. Constant. Okay, this is given. Second, it's a steady state. Okay, this is the pan. Okay, the thickness is 0.4 something. Diameter is 18 centimeter. Okay, this you can assume as plain wall. Like I said, all type of system in the universe can be divided into 3 coordinates. It's either going to be plain wall or a sphere or a cylinder. Okay, so this can be assumed as plain wall. Now, tell me which, it is written here, but tell me which formula we are going to use in order to study the heat transfer. constant and the operation is steady state. Steady state means temperature is not changing with time. Okay, and it's a plain wall. So plain wall had five equations, right? Okay. Thermal conductivity is constant. Which out of these three has thermal conductivity constant? All. Okay. Steady state operation. Which one? And the question also does not say anything about heat generation, right? This fan has no heat generation. So which formula out of these three? It's a steady state. Okay, so either first or third, right? The question is saying it's a steady state. Steady. Okay, so either this or this, first or third. Second equation is for transient. If you want to study heat transfer in a plane wall when the temperature is transient, then you use the second formula. But our numerical is saying that the heat transfer is steady. So either first or third. Okay? Then your numerical, this numerical is not saying anything about heat generation. Nothing about heat generation in this question when you read, right? So no heat generation. So this formula. Okay? Understand? Clear? So you read the numerical very carefully. Alright? So as an engineer, again, if I'm asking you to design something and I'm giving you that it's going to be a steady state, there is no heat generation in your material, right? The heat transfer is steady state. Then you design that by using this formula. Okay? If I'm asking you to design something and I'm telling you the heat transfer is transient and no heat generation, then you use this formula. Okay? Designing or studying. Okay? And then material or object. Okay. Okay. Another example. Also do the examples. Examples can come in your final exam. Okay? A 2 kilovolt resistance heater wire with thermal conductivity is given, diameter is given, length is given. By immersing it in water, assuming the variation of thermal conductivity of the wire temperature to be negligible. Thermal conductivity variation is negligible. So thermal conductivity is constant. Okay? Assuming the variation of thermal conductivity of the wire with temperature to be negligible. So thermal conductivity is constant. Okay? Obtain the differential equation that describe the variation of the temperature in the wire during steady. The operation is steady, the thermal conductivity is constant. So which equation? Out of these three, that wire here is a cylinder. Okay? Two things are given. The thermal conductivity is constant.
ไม่ยอมรับ
All right. Okay. Thermal conductivity is constant. All three has thermal conductivity constant, right? If the thermal conductivity was changing with temperature, we would use this variable conductivity, right? Second thing that is given in the numerical is that it's a steady operation. Okay? Steady operation. So either first or third. Right? Second is transient. But your question is saying that it's a steady state operation, right? Your question is saying it's a steady operation. Right? Your question is not saying there is any heat generation. If it's not saying, we will assume there is no heat generation. Okay? What is it? Okay, there is heat generation. It's given 2 kilowatt resistance heater. Alright? So, this equation. Understand? First you need to read the numerical very carefully. Then you need to understand which coordinate. Is it a plane wall? Is it a cylinder? Is it a sphere? Okay? Then write down what is given. Thermal conductivity is given, or it's changing with time, or it's constant. Is there a heat generation? If your question is talking about
มันตัวอย่างมันถอดตัวใช้สูตรไหน
like here, your question is telling you this much resistance, right?
สอนสอน
If there is a resistance, it's going to be heat generation, right? And this shape of wire is cylinder. It's not a
เอา
plain
สูตร
wall,
ว่าใช้สูตร
right?
ไหน
So you have to use your brains. Like if you're setting resistance in this is a cylinder. It's not a plain wall. Okay? Steady state, heat generation, thermal conductivity is constant. So this equation. Okay? Alright. Okay, read this question here.
Can we anchor the ball so that this side can see it?
What?
Can we anchor the Bible?
Okay. Better?
Thank you.
Let turn on the lights.
ไม่ทิศ
Can you see? Better? Okay, read this question very carefully. A spherical metal ball. It's a spherical coordinate. Spherical metal ball. Okay? Radius R, heated in an oven to a temperature of 600 degree Fahrenheit throughout and is then taken out of the oven and allowed to cool in an ambient air. The thermal conductivity of the ball material is known to be linearly with temperature. Assuming the ball is cooled uniformly from the entire but numerical, it's saying it's a sphere. So we are going to use the spherical formulas. This is very important. You have 1, 2, 3, 4, 5 formulas. Which formula describes the heat transfer in that question? Okay. So first, constant or varying? Varying, right? Right? You see the third line, the thermal conductivity of the bond material is known to vary. Varying is changing. It's not constant. Okay? Vary linearly with temperature. Temperature is also not steady. It's varying. It's changing. Thermal conductivity is varying. Temperature is varying. Once you know the conductivity is variable, you have only one option. Right? You understand why we are using the first equation? The conductivity is variable. Temperature is variable. You have two things. For variable conductivity, we only have one formula. First one. None of these formula, the conductivity is variable. Only first. So when your question is saying there is a variable conductivity, we use first formula. First formula in spherical coordinate. Okay? The object that you are dealing with in your numerical is spherical. This spherical and the conductivity is very clear. Okay. Now same thing, instead of plane wall we have rectangle because we are studying heat transfer in 3 directions. Okay, so we have x, y, z. Same energy balance equation, we just add y and z. Understand? Okay, and instead of plane wall we have rectangle now. The heat transfer is happening in x, y and z direction. Okay, x, y and z direction. So the energy balance equation we also include y and z. Y and z. Okay. When you are writing the rate of change of the energy content, you also add in the mass x, y, z. Okay. Here as well, when you are calculating the volume of the rectangle, x, y, z. Okay. Input this and this in the equation above, you get this. Take the limit, same derivation that we did for plane wall, now we are doing for rectangle. Understand?
ทุกคนได้หรอเบียร์
This was the plane wall. The
Yeah,
heat
look at
transfer
me,
is
yeah.
happening in one direction.
กูชอบ
Now we are studying heat transfer in 3 dimension. So this plane wall is now the rectangle. Okay. We will also add y and z. So qx plus qy plus qz minus qx plus del x minus qy plus del y and z plus del z. Okay. Here in the area you have only del x. In 3 coordinates, del y, del z. Okay. Same here. Okay. And then you follow the steps, same steps here. Okay. Taking the limit and then coming up with these equations for plane wall. Now we are deriving for here. Now we are deriving for rectangle. Okay, 3 dimension. Same. Now we are taking limit of del x, del y, del z. 3 coordinates. Okay. Same. We have 5 formulas for rectangle. Like we had 5 formulas for plane wall. Plane wall and rectangle are same. In plane wall, the heat transfer is in one direction, only x. Rectangle is same, but in 3 dimensions. Okay. Same formula, but we also have x, y, z. Okay. X, y, z. Same formula, like the plane wall. Okay. Now you will see questions in 3 dimensions, and they will talk about what is variable, what is constant. You read that numerical very carefully and choose which equation describes the heat transfer. Okay? So in your exam, in the A4 paper, write these equations. Or you can only write first equation and then you can see, like if the conductivity is constant, just remove the K. Okay? Or if you want to write all, you can write all. So this is for rectangle. This is for cylinder. And this is for sphere. Okay. Whenever you are solving something, any heat transfer problem in real life, you must have some conditions. Initial conditions, boundary conditions. Initial condition is like the initial temperature of the room is 20 degrees Celsius. If I am telling you, you have to design something and the room temperature is 20 degrees Celsius, this is the information I am giving you initially before you are starting your study. So this is called initial condition. Okay. Boundary condition is, I am telling you what are the condition on the boundary of that object. If you are designing a window and I am telling you at the boundary the temperature is this, or at the boundary the heat flux is this. So these are boundary conditions. Initial and boundary conditions you have before you start studying the heat transfer. Okay. Alright. Initial condition is a mathematical expression. Initial condition is a mathematical expression for the temperature distribution of the medium initially. Initial temperature of a system before the heat transfer occurs. Before heat transfer is happening, before you are studying, whatever information I am giving you, okay, it will be either initial condition or if I am telling you the condition on that object, it's going to be the boundary conditions. Boundary conditions are specifications that define the behavior of a physical system at its boundary or interface with the surrounding. If I am telling you at the boundary the heat flux is this, or at the boundary there is an insulation, so no heat transfer is happening. So this is boundary condition. Okay. If this is a window and I am telling you outside is an insulation layer, so that means the heat transfer is not happening from outside to inside. Right? So this is a boundary condition which is happening on the boundary of the object. Initial condition is, I am telling you the initial temperature of the room or initial temperature of outside. That is initial condition. It's not on the object. So These conditions dictate how the system interacts with its external environment and influence the transfer of heat, mass or momentum across its boundaries. In simpler terms, boundary condition describe what happens at the edges or surface of a system, okay, guiding how it interacts with the outside. So there are mainly 6 types of boundary conditions. 6 types of conditions that can be applied on the boundary of your interested object. Okay, these 6 conditions can be applied if you are studying a plane wall or a cylinder or a sphere. Okay, specified temperature, specified heat flux, convection, radiation, interface, and general flux. So we are going to study these, okay, one by one. First is specified temperature boundary condition. If this is a window, okay, this is a window, and I'm telling you the temperature here is 150 degrees Celsius at this point, and here is 70 degrees Celsius. So this type of conditions is a boundary condition. And which type of boundary condition? Specified temperature boundary condition. Okay? Before you study the heat transfer, I'm already telling you at this side of the window or any object, the temperature is 150. The outer side is 70. So this is specified boundary condition. Okay? So you can write down the temperature at, this is the coordinate, 0 at time small t is T1, and at the coordinate L, 0 T is 150, L T is 10. So this is specified boundary condition. Boundary conditions we apply at the boundary of our object. Okay? So the temperature of an exposed surface can usually be measured directly and easily. Therefore, one of the easiest way to specify the thermal condition on a surface is to specify the temperature. For one-dimensional heat transfer through a plane wall of thickness capital L, for example, the specified temperature boundary condition can be expressed as this. Okay? You write down the coordinate and then you write down the temperature. Second is specified heat flux. Okay? Heat flux, all the boundary conditions again will be applied at the boundary. So heat flux boundary condition, let's suppose I'm telling you the heat transfer from here to here is by conduction, let's say, okay? So I'm telling you the heat flux at this boundary and the heat flux at this boundary before you study your heat transfer. When there is a sufficient information about energy interaction at a surface, it may be possible to determine the rate of heat transfer. Okay, if I know the temperature of this room is this, okay, you're designing your window, so I can tell you before you study your heat transfer that at the boundary of the window, inside the boundary, the heat flux, okay, the heat transfer is this. Okay, the value is not given, but the point is, if I'm telling you the heat flux, the boundary condition is this heat flux. Okay. So the heat flux in the positive x direction anywhere in the medium, including the boundaries, can be expressed by Fourier's law of heat conduction. Okay. Insulated. Again, before you start studying your heat transfer in this window, right? I am telling you that the inside of the window is insulated. Insulated means no heat can enter, no heat can leave from this side. Okay? So I can apply insulated boundary condition on the boundary of the window. Okay? All these objects are plane wall, right? The figures given here are plane wall. They can be spherical, they can be rectangle. Some surfaces are commonly insulated in practice in order to minimize heat loss. Okay? Then the boundary condition on a perfectly insulated surface can be expressed as this. Insulated boundary condition. So how do we define that? We are writing heat flux and we are equaling it to 0. When the heat flux is 0, it means that there is no heat entering or leaving. It's an insulated boundary condition. Okay? Alright? Thermal symmetry. If you are studying heat transfer in an object which has thermal symmetry. Okay, what you can do is, okay, you have this type of a window, okay, it's very thick and there is a thermal symmetry. The temperature this side and this side is going to be same. Okay, there is symmetry. Some heat transfer problem possesses thermal symmetry as a result of the symmetry in the imposed thermal condition. The two surfaces of a large hot plate of thickness L suspended vertically in air is subjected to the same thermal condition, and thus the temperature distribution in one half of the plate is the same as then in the other half. Okay, let's suppose this is a plate. Okay, this is a plate and I extended it in some heat. Okay, or I extended this plate in this room. I know the room temperature. Alright, so the heat transfer from this side and this side of the plate is going to be same. So instead of studying heat transfer from the both side, I can just study heat transfer from one side, okay, because this is thermal symmetry, and then I can just apply the same heat transfer on the other side. Okay, you see the slope here in the middle is 0. There is no temperature change in the middle. So it depends, it's very rare actually, but it depends. If the object has some thermal symmetry and from both sides the heat flux are same, then you can apply the thermal symmetry boundary condition. Okay. You see this temperature change in the middle, L by 2, yes, 0. So, direction of heat flow at any point in the plate is towards the surface closer to the point, and there is no heat flow across the center plane. Therefore, the center plane can be viewed as an insulated surface. Again, this you will understand when you do the numericals. Okay, now we have numericals. Okay. Consider an aluminium pan used to cook beef stew on top of an electric range. The bottom section of the pan is L, 0.3 centimeter thick and has a diameter of 20. The electric heating unit on the range top consumes 800 watt of power during cooking, and 90% of the heat generated in the heating element is transferred to the pan. During steady operation, the temperature of the inner surface of the pan is measured to be 110 degrees Celsius. Express the boundary condition for the bottom section of the pan during the cooking process. So, is there any boundary condition given already in the question? Any boundary condition? Is there any boundary condition given? Initial or boundary condition? Can you tell if there is any initial or boundary condition given? So all of the items given in this numerical is before we study heat transfer, right? So there must be some initial or boundary condition. Can you identify any initial or boundary condition? There is one initial boundary condition, which is initial temperature, right? There is one temperature given, 110 degrees Celsius, right? I told you when you are reading a question and the temperature is given, it's already initial temperature, right? So 110 degrees Celsius is the initial temperature, and they are saying the heat is coming from here, right? And everything is given. The power that oven is consuming, right? If you have this, and if you have the area of this pan, you can calculate how much heat flux, right? So heat flux, it's a boundary condition. the given temperature is an initial condition. 2 point, not 2 point, 2.6 this one. Okay. The temperature at the inner surface of the bottom of the pan is specified to be 110 degrees Celsius. Then the boundary condition on this surface can be expressed as this. So this is your one initial condition, and they have told you the heat transfer rate and the bottom surface area. So this is a heat flux. Two boundary conditions. Okay. First, the question is telling you the pan, the temperature at that point is 110 degrees Celsius. So this is the initial temperature. Okay, TL. Second boundary condition, they are telling you how much watt that oven is consuming. Right, 90% is given. Right, the question is saying 90% is given, and then they have also given the area of the pan. When you have the area and when you know how much heat is getting transferred, you can calculate the heat flux. So, heat flux boundary condition. Okay. This boundary condition is heat flux. This is initial temperature here. This one. Specified heat flux boundary condition is given, and this first and second. Okay. Initial temperature, specified temperature. Okay. Alright. Then there is convective boundary conditions. So boundary conditions, again I am repeating, are the conditions that are given before you study the heat transfer. So if I am telling you that whatever heat is coming, okay, inside from the convection is equal to the conduction happening, then you can use this. You can apply this boundary condition. It means no energy is lost. Okay, in between. Whatever is coming from the convection is going to transfer by conduction. There is no loss of the energy. Okay. Alright. Like in here, the convection will happen from here to here, from the air, right? And conduction will happen inside this wall because it's solid, right? So convection equals to conduction. There is no energy lost on the surface of the wall or anywhere. Whatever energy is, heat is coming from convection, it is equal to conduction. Okay. Now look at this example here and tell me which boundary condition can be applied. Steam flows through a pipe shown in figure this at an average temperature. Temperature is given 200 degrees Celsius. Inner and outer radii of the pipe are given, and the outer surface of the pipe is heavily insulated. There is an insulated boundary condition, if you remember. If the convection heat transfer coefficient on the inner surface of the pipe is given, express the boundary condition on the inner and outer surface of the pipe during transient period. So two boundary conditions are already given. Which are those? Insulated is given.
And
So insulated boundary condition is this. This is given, right? The question is saying the outer side is insulated. Insulation. Okay. Then temperature, specified temperature, boundary conditions. Third, they are asking us to express the boundary condition on the inner and outer surface of the pipe during transient period. So this pipe, insulation is this. Let's suppose we applied some rubber over here. Okay, this is thick, this is solid, and there is a steam. Steam is flowing. So heat transfer from here to here will be by convection. Heat transfer from here to here will be by conduction. And there will be no heat transfer from here to here because it is insulated. Right? So convection is going to be equal to conduction. This is the third boundary condition. Understand? here, R2. There is two radius, R1, R2. So insulation boundary condition here, R2. Okay? The heat transfer is 0. No heat transfer from here to outside. Okay? Specified temperature. So one temperature is given, T infinity. This temperature, T infinity. This convection boundary condition.
Tôi đến với bạn.
Okay. Heat transfer is a steam, it's flowing from here to here by convection. Okay. T infinity to this, let's say TR1. Okay. From here to here it's a solid by conduction only. So conduction. Okay. This is the formula for convection. This is the formula for conduction. Okay. Be very careful with the coordinate R1. R1. R2. Sorry, it's going to be R1. R2 is here. There is no heat transfer here. So it will be R2. T infinity to T R1 and the conduction is happening from here. Here. R1. Understand? 3 boundary conditions in total. When you read the question, steam flow through a pipe, average temperature, specified temperature boundary condition 1. Then second boundary condition is insulated. Okay? Second boundary condition. Third, they are asking you to express the boundary condition on the inner and outer surface. So we know the heat transfer, since it's moving, is going to be by convection and then conduction. Right? Coordinates again. This is R1. So T infinity to T R1 and the conduction will start from here. Okay? So R1. R2 is insulated. R2 is insulated. Okay? Alright. Radiation boundary condition. In radiation boundary condition, what will happen? The heat transfer from outside to this wall is by radiation and is equal to conduction. When I'm saying it's equal to, it means whatever heat is transferring by conduction is going to transfer by conduction now. There is no loss of heat. Okay? So this is radiation boundary condition. Alright? Interface boundary condition. When you are using two material and you have attached those material. Okay? Let's say I am using one copper, one nickel. Let's say, right? And I attach those material A and material B. the conduction from here to here is going to equal to conduction from here to here. But this is a very tricky boundary condition. This you can only apply when the two bodies in contact must have the same temperature. The nickel should be like 20 degree and the copper should be 20 degree as well. An interface cannot store any energy. Like I said, on the surface, when you are studying heat transfer on a wall, there is no energy on the surface of the wall, right? So same, the interface cannot store any energy. An interface cannot store any energy, and thus the heat flux on the two sides of an interface must be the same. Since they are different material, but both are solid, so the heat transfer will be by conduction only, right? Okay? No convection, only conduction. Alright. Generalized boundary condition. Okay? If I'm saying the heat transfer, let's say there is some heat generation here, and the heat transfer from inside to the outer surface will be by conduction, it's a solid, and then from here to outside will be both by convection and radiation. Okay, so this is a generalized boundary condition. Okay, so if I'm saying do it yourself, this can also come in your exam. You have to do it by yourself. If you have any doubt, then ask me in the next class. Okay? But try by yourself. You have the book, these are the examples. They are explained very well in your book. Okay? I'll try to explain as much as I can here, but there are so many examples. So you have to also study by yourself. Okay, now we have numerical. Consider the south wall of a house 0.2 meter thick. Okay? The outer surface of the wall is exposed to solar radiation and has an absorptivity is given 0.5. The interior of the house is maintained at T infinity 1 while the ambient air temperature outside remains this. The sky, the ground and the surface of the surrounding structure, and this location can be modeled as a surface and effective temperature of sky for radiation exchange on the outer surface. The radiation exchange between the inner surface of the wall and the surface of the wall's floor and ceiling it faces is negligible. The convection heat transfer coefficient on the inner and the outer surface of the wall is given. The thermal conductivity is given, emissivity is given, assuming the heat transfer to the wall to be steady and one-dimensional, express the boundary condition on the inner and outer surface. So we have to define the boundary condition, okay? This diagram only explains everything. Inside the house there is an air, right? So heat transfer from here to this boundary is by convection. This is wall, it's a solid, so the heat transfer inside the wall will be by conduction. Outside is radiation plus convection, right? So outside will be, so there are two boundary conditions. Can you take a guess? There are two boundary conditions. Tell me from here to here, which boundary condition? And then from here to outside, which boundary condition? convection plus radiation. Okay? So inner surface, two boundary conditions. First is this convective boundary condition. Understand? Convection is happening from inside the house to the wall. And the second is this generalized. Okay? This two boundary conditions. Inside is convective boundary condition, outside is generalized. Understand? So at the beginning of this chapter, we started defining the equations for temperature, right? In one coordinate, three coordinates, in a plane wall, in a rectangle, in a sphere, right? Second part of this chapter was to study the initial and boundary conditions. Okay. Now, from this example onwards, example 210, we are going to combine both. Okay. First, we are going to read the numerical very carefully and understand which differential equation. Okay. So, like in this example, the figure is a plane wall. Okay. So, we have to carefully decide, okay, which differential equation for plane wall we are going to use. Second part of this numerical will be which boundary conditions are given. And then the third part is we have to solve the differential equation by using the initial and boundary conditions. Okay. So the first type of numericals that we did, we are trying to find, right, what kind of differential equation we are going to use. If the conductivity is steady, if there is a heat generation, so we are figuring out, right, which differential equation based on the coordinates. Second part, we are studying the numerical and we are trying to find out which boundary and initial conditions are given, right, or apply, right? Now we are going to combine both, okay? So in this example, consider a large plain wall of thickness L, 0.2 meter, thermal conductivity is given, surface area is given, the two sides of the wall are maintained at constant temperature T1, T2, okay? Determine variation of temperature within the wall and the value of temperature at x equals to 0.1, rate of heat conduction through the wall under steady conditions. So first tell me what boundary conditions are given in this question. Heat, no. Specified temperature boundary condition is given, right? At T1 and T2, right? The coordinates are T0 and TL, right? At T0, temperature T1 is given, at TL, the temperature T2 is given, okay? So this is specified temperature boundary condition. So the A part of this question, determine, A is asking variation of temperature, okay? This we cannot find out with boundary condition only. So we need to know which differential equation, okay? Which differential equation for this? So this is a plane wall, right? And it's in one dimension. So which, this one? Out of these three, which equation, differential equation, defines that numerical? Okay, so we have these three. This one, okay. So first, see if the thermal conductivity is variable or it's steady. Steady, okay. So first we know our object is a plane wall, it's in one dimension, okay. Thermal conductivity is steady. So we can narrow it down here, okay. It's steady state, so either 1 or 3. Is there any heat generation? When you read the numerical, is there any heat generation? Are they talking about any heat generation? No, right? So, equation 3. Okay? So, we have the differential equation and we have two boundary conditions. Temperature, specified temperature, two sides. Now we are going to solve the differential equation. A part is saying determine the variation of temperature within the wall of temperature at x equals to 0.1. B is asking rate of heat conduction through the wall. Okay. understanding which equation we will use, right? The second part of this chapter was understanding which boundary conditions are given in the numerical. From now on, we have to use this differential equation to understand the heat transfer. Okay? Like I said, you are a manufacturer engineer, right? I'm asking you to design a window, right? And I'm telling you the window is a plain wall and there is the thermal conductivity of the material of the window is constant, right? There is no heat generation in the window, right? You will use this differential equation to study the heat transfer. But in order to study the heat transfer in that window, you also need some boundary conditions. Okay? So I will also tell you the temperature inside the room is this and outside is this. Okay? The first part of this numerical is asking the temperature at somewhere 0.1 meter. Okay? Temperature at 0.1 meter. And rate of heat conduction through the wall under steady condition. Rate of heat conduction. So rate of heat conduction is going to be by conduction. Okay? This we can find out by Fourier's law of heat transfer. Okay? So in order to know the temperature here, right? Variation of temperature here. This thing tells me the temperature distribution in this wall. In what dimension, right? From here to here. Okay? I need to know the temperature at here. So I need to solve this. Okay? Every heat transfer problem will have at least two boundary conditions. So I have these. So if you have a software, you can design a wall like this. Okay? You can specify the boundary conditions and the software will solve it for you. Okay? But now you have to do it by hand. So we will start solving this differential equation. We will use these boundary conditions. Okay? And we need to come up with one equation that is a solution for this problem. Okay? I'll walk you through step by step. So we need to find one solution. General solution we call it. So this equation is for any plane wall, right? We need to find one equation which is only for this condition, only for this wall. Okay? This equation is for any plane wall which has thermal conductivity constant and no heat generation. But we need to find one equation which is only applicable for this wall, which has these boundary conditions. Right? So how will we do that? We will try to differentiate this first. Okay? So let's say this is equation 1, this is 2. Okay, integrate it once.
ใช่ไหม
Okay, so what we did, first you read the question, right? This is a plane wall, and the plane wall has constant thermal conductivity, the plane wall has no heat generation. So this is a normal equation that can be applied to any plane wall which has these two conditions, right? But in this case, the plane wall has these two boundary conditions. Now we need to study the temperature inside the wall, right? In this case, specifically at 0.1 meter. Okay? So if you want to study the temperature in this wall with these conditions, you need to have one equation, one general solution that is only applicable for this wall. Okay? How will you do that? You integrate it once, you integrate it twice. You have two coefficients, C1 and C2. Now you use these boundary conditions, you input these boundary conditions and you find out C1 and C2. Okay? At the end, you are left with this equation. This is a general solution. This equation is only for this case. Okay? This equation is only for this case. Right? Now what I will do, in case of X, I will input 0.1 meter because this question is asking the temperature at 0.1 meter. So I will put 0.1 meter here, T2 is given, T1 is given, L is given. So I will know temperature at 0.1. Understand? Can you find out? Can you input the values and tell me the temperature at 0.1? You understand, right? What is happening? Can you input all the value and tell me temperature at 0.1? Value of X is 0.1 meter. have any doubts, you can ask.
Xong rồi bây giờ
Ủa, thì mình xử lý dịch sau.
Rate of heat conduction. Heat transfer inside this wall is by conduction only, right?
Bây giờ chị này và nhìn nó nhìn nó gần mình nhìn Part B, they were asking rate of heat conduction. Conduction, right? This is the Fourier's law of heat conduction. Okay? dT over dx can be written as C1. Value of C1 is this. So we input everything here. C1 is this. Thermal conductivity is given, A is given, L is given, T2, Tn is given. Any questions? but the boundary conditions are different. A, B, C. Is this enough or do you want to study more for today? Is this enough or you want to study more? Is it okay? Do you want to solve another question or next time? What? Okay, let's solve two questions and then this you try yourself, this three try yourself. This we will start from next question.
เขาพอจำได้เลยว่า
ก็ที่ดีนะที่ดีอันนี้คือ
อันนี้ค่ะอันนี้ไม่ได้
อันนี้ที่เรามาพวกมันดีเลย
เอาไม่ออก
Explain this. To 11 you can do. If you have any doubt in numerical 211, you can ask me next time. Okay? Next class. I'll solve to 12. Can I move? Okay. Consider the base plate of a 1200 watt household iron that has a thickness of 2.5 centimeter. Base area is given, thermal conductivity is given. Inner surface, thermal conductivity is given, thermal conductivity is constant, not changing. Okay. Inner surface of the base plate is subjected to uniform heat flux. Okay. This side subjected to uniform heat flux generated by the resistance heater inside. This is the heater and this plate is subjected to heat flux. Outer surface loses heat to the surrounding at T infinity by convection. This loses heat by convection. Taking the convection heat transfer coefficient is given. Disregarding heat loss by radiation, no radiation. Obtain an expression for the variation of temperature. Variation of temperature means we have to use first the differential equation and find out a solution only for this condition. Okay? Obtain an expression for the variation of temperature in the base plate and evaluate the temperature of the inner and outer surface. So we have to find out the temperature inner and outer surface. This side, this side. So this plate can be assumed as A1. Okay? transfer that is happening from here to here, heat flux, right? This is subjected to constant heat flux. Inside conduction, outside convection. Okay. Now tell me for plain wall when the thermal conductivity is constant, right? What else is given? Steady state, right? It's steady state. And thermal conductivity is constant. Which equation for the plain wall we are going to use? Okay? That iron is like a plain wall. That iron has constant thermal conductivity. The thermal conductivity is given, it means it's constant now. Okay? That iron has no heat generation. Right? And what else? Yeah, no heat generation and constant thermal conductivity. This equation is a general equation for any plain wall whose conductivity is constant. Okay? And there is no heat generation. But for that case only, we need to find one equation. Okay? One solution that is only applicable for that iron. And it's a plain wall. Okay. Boundary conditions. First is heat flux, right? Okay. The question is saying that the heat transfer outside is happening by convection. So we use this boundary condition. We apply this boundary condition. Okay? Convective boundary condition. Okay? Second boundary condition that is given is heat flux. This. So let's read the numerical again. The inner surface of the base plate is subjected to uniform heat flux. So heat flux boundary condition. Okay. Yes. Second is the heat losses to the surrounding by convection. This you can find out, right? Q is given, area is given. So you can find out this.
vừa tắm cam rồi.
ยังจริงแล้ว
เชื่อไม่ได้จริงนะ
มีให้
จังไป
ไปไหน
ฟิน
Học bài, học bài mới
สมัค
sỏi.
รเล่นฟรีสมัครกีฬา
อ๋อเอาเดี๋ยวนี้ไปกีฬาแล้ว
ไม่มีตังค์
Mình liền cái luôn. Dạ, dạ, dạ,
อ๋อ
mình liền.
ไม่คุ้ม
Mình nên liền mà còn mình.
ช่วงเดือนว่างสายผมลงฟรี
อะไรนะ
พอว่างสายยาวก็ฟรีลง
อ๋อไม่ได้ไปเลยอ่ะไม่ได้แบบขี้เกียจอ่ะ
สั้นๆนะ
สั้นเลยแบบตรงๆเลยอ่ะไม่แบบตรงๆเนี่ยขี้
This
เกียจ
can
เล
be
ย
replaced by C1. Okay. So basically we have to find the value of C1 and C2. This can be replaced by
แล้วอาจารย์ก็บอกอะไรก่อนหน้านี้บอกว่าอาจารย์จะพยายามไม่ค่อยขาวนะครับรั่วฟังรั่ว
okay. I request you to take a picture or write down this numerical here because I'm not following the same way that your book has mentioned. I have solved my different version. This is the book thing, this is my
ก็รู้ว่ามันเป็นเราเนี่ยก็รู้ว่าเซฟอย่างนี้
เสียดีใครเรื่องด้วยเพราะว่าเนี่ยผมบอกว่า
มีคนบอกที่มาก็บอกคนที่โดยทางการที่เซฟที่มองที่เชิงครับคนที่ตั้งมาที่ต้องการเป็นรูปแบบ
ไม่เย็นนะ
เป็นแบบก็ได้สุดที่ที่ทำได้ที่ต้องรวมของใส่ใจใส่ใจก็จะต้องก็ต้องสิ่งที่ไม่ได้เป็นที่เราเป็นของปกติที่รู้สึกว่ามันก็ต้องความหวังเราต้องรู้สึกที่เอาที่สุดก็เป็นการทำงานที่ลำบากก็ออกมาเลยเป็นลำบากไม่ต้องฟ้าเลย
ไม่กำลังใจนะ
ผมเพราะว่าเราไม่เชื่อผม
แอร์ตามนี้แอร์มันเล็กนะ
แต่เป็นตัวเองแบบก็เพื่อผมฟังมันไม่ได้บอกว่าเราต้องดูความเป็นเราที่นั่นคือโค้ชต้องการทำที่ข้างหลังก็แบบ
So we calculated the numerical, right? We can see it's a plain ball, right? So we draw a diagram of the plain ball. This numerical is saying that when you plug this iron to a socket, the electricity goes inside and some heat fluxes applying this side of the plane, okay? And outside the heat is losing by convection. This everything is given in the question. So you can see it's a plain ball, right? Thermal conductivity is constant. The value of thermal conductivity is given. That means it's constant. Okay? So you go back and see in your notes for a plain ball where the thermal conductivity is constant, which formula should I use? Okay? So you use this formula.
เยี่ยม
When the
เขา
thermal
เตรียม
conductivity is
ภาพพิเศษ
constant.
ของอาจารย์ก๊อฟเตรียมปากกาทำว่าเราเลยเราต้องเตรียมปากกา
Then, in order to get one expression, which is only for this condition, you need at least two boundary conditions. Every question should have at least two boundary conditions. So you read that numerical again, and you see there are two boundary conditions. First is it is saying there is a heat flux at this point. So heat flux boundary condition. Second is saying that the heat is lost outside by convection. So convective boundary condition. Okay? So you have this given, this given, this given. Now you have to solve it. You have to find out, obtain an expression for the variation of temperature in base plane. In this case, you have to obtain an expression. Okay? So how will you solve? You first start to integrate it. You integrate it once, this comes, integrate it twice, this comes. Okay? Now you utilize the boundary condition in order to get one expression. So you utilize this boundary condition, heat flux. Okay? Input C1 here, this everything is given. In your book, they are doing it in different way. So you can follow that or you can follow this. Either way is fine. So you have the value of C1. Alright? Then you use the convective boundary condition, input everything, you get the value of Tn. They are also asking temperature at the inner and outer surface. Inner surface is this T0, outer surface is Tn. So you have to also find T0 and Tn. So we have found Tn here. Okay. Now you have value of Tn 5, you in 6. 5 is this, 6 is this. You input in 4. 4 is this. You input everything in here, you will get the value of C2. Okay? Every time when we are solving this, we are finding out C1 and C2. That's what we are doing. Okay, so it's just calculus actually, nothing. Okay? You have C1, C2, you have Tn, you have T0, you don't have T0 yet. Yeah, just input T0 here. You have the value of H, you have the value of T infinity, you have the value of K, you have the value of C1. C1 you have value, yeah. So you can find out T0. Understand? Okay. So you either solve this numerical by this way or in your book it's different. Okay. I find it a little confusing. So if you can understand that, it's okay. You can solve it by that way. This one here. Okay. And I solved it in my way. So you can either use this or solve it. So I'll revise what we did. First we started with finding out a differential equation, right? For three shapes, a plane wall, a rectangle, a sphere. Okay. First we find out in one dimension. Second part was in three dimension. Okay. So in one dimension, these kind of, okay, steady state, transient no heat generation, steady state no heat generation. Okay. Then we find out in cylinder and sphere. Okay. Then we find out in three dimensional. The plane wall became rectangle. Then we study boundary conditions. Okay. Alright. Example 211 you try to solve by yourself. 212 I solved. Okay. 213 you try. 214 you try. 215 you try. 216 I will solve next Monday, and then we will start heat generation. Okay. In your assignment, you go through the questions, whichever you can solve right now based on what we read. You solve it and you submit. Okay. And of course, next class when we complete the whole chapter, you can submit again. Okay. If you have any questions, you can ask now or next Monday. That's it for today. Thank you.
About paper and the usual exam, if it has to be written exam 5 and 20 and you can tell you. เป็นมืออย่างเดียวเลย